Yeah. 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 So last talk of the workshop. First, I would like to say thank you for having me here, for letting me talk. And it's been really nice 2 days because this is the first time I've come to the US and it's been super cool. So I'll be talking about the framework that Alexia had mentioned already, the bipartite quantum energetics and others from my group, Leah. And this is something that I would like to talk about and basically end the workshop. So the title of the talk is Closing the Optical Bloch Equations in Waveguide QAD. Now, this is also I feel it's very related to the question of Spencer's that we had, like if you have a time-dependent Hamiltonian, how do you relate it to, the external drivers that are really at play? So this will be a really nice connection there. And what I'll be talking about is the dynamics and the energetics. Okay. But as this is the last talk, I would like to first give a small overview about what we are trying to do really, right? So most of us where we start with, we want to analyze some protocol or some task that a quantum device wants to do. So we want to make some analysis on things like superconducting circuits, trapped ions, etc. So what we do is we model it as a system interacting with external sources, like external fields, and it could be like baths or what. Yesterday we saw that for example, in Andrew's talk, in Alexia's talk, that we should throw away thermal baths, and it's really useful to talk about just quantum resources that are interacting with your system instead, right? And from here we can go to some kind of energetic description or some description about the information theoretical analysis. For example, in Maria's talk, we saw that it's very useful to have the complete solution and then talk about the measurement results that you can get from your quantum probes, right? And you can actually get some quantum advantage there. And so what's important is when we model these systems, we should have a closed system solution. We should have the solution for the system and all the fields around it. We don't trace over the bath or the fields that are there. And as Maria has shown, that we can use the collision model to solve these dynamics which are similar to this, a small system interacting with a big field. And from this, you get access to subsystems plus the correlation information, which we then use to make to do the energetic analysis and to do to talk about other measurements and things like that. Now, Alexia talked about bipartite quantum energetics, where if you have noticed, there were separation of correlations and the subsystems, and we always talked about both the subsystems, right? And so this framework really requires you to have the complete solution, one. And the second thing is this framework, as Alexia had mentioned already, it's a very symmetric framework, which also allows you to measure the energetic quantities that are there, the heat and the work. So you can measure the heat and work for both the small system that you're thinking of and all the fields around it. Okay, so that's something that kind of motivates us using bipartite quantum energetics. Now that I hope you, from the different talks of Leah, Alexia, Maria, Nicolo, I hope it's motivated that we should get the complete solution and we should try to use this bipartite quantum energetics. So the question arises, if you heard the talks today, that how are these quantities related to the regular quantities that we think of with the baths? Like for example, in Bibek's talk, in Mateo's talk, we saw there are baths around. And how does the bipartite definitions of heat and work relate to these regular definitions? So that's what I'm going to do today. And this is what basically our group has done. And these are some photos of our group members who participated in making this comparison. This is Alexia, and these are all photos from our outings, basically. So how do we make this comparison? Okay, so the first thing to make the comparison is to talk about what approach do we compare with, right? What's this popular approach that we can compare with, right? So one popular approach that is used to define heat and work, because there are a plethora of literature on what is work and what is heat. So we have to choose one popular one. So one is that popular one is which started in the 1980s by Aliki, where you define Alitsky. Alitsky. And it's basically uses work. It defines work and heat using Lindblad master equations, and this is an open system method of defining work and heat. And what we use is essentially to define the thermodynamics on the optical Bloch equation, and that's the setup that we'll use. This is something that Alex had briefly mentioned, and also mentioned that I'll be talking about the optical Bloch equations. So I'll be talking about it. Now, the second thing that is needed to make this comparison is the platform on which we compare. So the requirements to make the comparison are, one, the platform that we use, we have to get like a isolated bipartite and exactly solvable model of your interacting systems. The reduced dynamics of the subsystem should compare with the approach that we're using. So in this case, the optical Bloch equation. And the platform that does this for us is something that we have already seen in the workshop. That is the one-dimensional atom that Nicolo spoke about, I think Maria also spoke about, right? And this, in the one-dimensional atom, really obeys the optical Bloch equations. So the only thing that is left after that is really solving the dynamics and doing the energetic analysis. And then after this, we can really compare with the analysis of the energetics that's already done for the optical Bloch equations. Okay, and the paper that is used to do the energetic analysis of the optical Bloch equations is by Cyril. It's here, the Cyril Helva, thermodynamics of optical Bloch equations. Okay, so first I would like to start by giving a small recap. This section might have things that we already know, but this is like a reminder section. I'll talk about the optical Bloch equations and the bipartite quantum energetics here. So let's just start. Again, we want to model this quantum devices. The way it's done in the open approaches is that we have a system and it interacts with a classical source, which drives the system unitarily, but also the system dissipates into another path. So there is some external driving and there is some dissipation, right? And here the system obeys the optical Bloch equations, and this leads to the open system energetic. So we'll talk about it. The optical Bloch equation looks like this. This is something, the Lindblad form that we saw in Ronnie's talk, in Vivek's talk, right? So we have this. So what are these optical Bloch equations? So in the optical Bloch equations, the system is a qubit, one, as you can see here. And there are some assumptions made on this bath that the qubit interacts with. So first of all, this bath is thought of as a multi-mode bosonic field with some temperature beta, or the average excitation number could be n bar that I've used here. It's a flat reservoir. That means the coupling strength is the same with all bath frequencies. Okay. And the very important point here is the correlation time of the bath is this tau c is much lesser than the time scale of the qubit population in the excited state, the gamma inverse. Okay, so here I want you to notice this in the optical Bloch equation, there is driven unitary dynamics, where if you notice this hd is the driving term, which is time dependent and it's given here. It depends on it's with the sigma plus sigma minus operators, and there's this dissipative dynamics, which has the temperature involved at the n bar. Okay, now let's talk about the energetic, the first law using the optical Bloch equations. So the way it's defined is the internal energy change of the qubit is given by the energy inputted by this external drive, that's the work, plus the energy change of the bath, that is the heat. So all the energy that's dumped into the bath changes the energy of the bath, and that is where the heat comes from. Okay, so this energy change of the bath to define heat is the main point of the energetics of the optical Bloch equations. And what the way of defining heat this way does is that in the second law, when you talk about the second law of thermodynamics, where you have the Voigtnamen entropy change of the qubit, it minus the beta q, this is like a Clausius form, which is greater than 0. This gives you the second law of thermodynamics, essentially. So now that this is the very, it's not too hard to understand this. I've described to you the energetics of open system approaches in essence. So the question arises, how do we close this dynamics? Like, first of all, what does it mean by closing? By closing, we mean we need some external drivers. We need to model this external driver and the bath, and we need all information about everything that is involved here, right? So the way we do it is using the 1D atom that we've already seen, where there's a qubit and there's a propagating field. The field comes, interacts with the qubit, leaves as in a different state. The Hamiltonian, and this system is isolated. That's very important. We have a bipartite system that's isolated from everything else. Okay, so here the Hamiltonian is given by the Hamiltonian of the qubit plus the field plus the interaction term, and the interaction is essentially this exchange interaction, the James-Cumming type interaction here. Okay, and yeah, the plus point about using the 1D atom is this can be solved using both the open approach and the closed approach that I'll show you soon. So we saw in Maria's talk that such systems can be solved using the collisional model. Okay, and the way we get to the optical Bloch equation is by specifying the kind of input state that we use. So I have already shown you what kind of interaction we are using with the field. Now, if we use a specific kind of input state of the field, we can get that the reduced dynamics of the qubit is the optical Bloch equation. So to solve the state that is used is this coherent thermal state. And the thermal state is very special here because it's temporarily uncorrelated. Okay, so you can define discrete modes, temporal modes, and each temporal mode has this thermal state. But also this thermal state is displaced by a certain alpha. Okay, so in the collisional model, the general scenario is time is discretized, then temporal modes are defined and turned into discrete collisional units. So each the bath unit or the field unit comes, interacts with the qubit, and leaves as a output state. Okay, so here, if you solve for the qubit dynamics using these coherent thermal states where the thermal state is temporally uncorrelated, you get the optical Bloch equations, as you can see here. What is important is that you see this driving term, it has the omega, the power with which you drive. This depends on the displacement of your thermal state, the alpha here. Okay, now I'll try to make it more clear in the next slide. So can I
ask a quick question here? So in the open system approach, you had a bath and a drive. Okay, so now with this model, everything is
in the input state. Exactly.
So there you have both like the bath and the driving.
Exactly. And this is what I'm going to show next.
Is it? I mean, it almost looks like I'm being stupid right now, but it almost looks like the energy of the field is infinite. Like,
here we take, so it depends on how long you interact. So here we take a flat field. It's like a toy model almost. But yeah, we take a flat field so that dynamics becomes easy to solve for the field also. But yeah, you can still have like a envelope where you define with a particular input energy. Just give me a second. You have a constant frequency. Yeah.
Frequency or amplitude?
You have a particular amplitude at a particular frequency with which you drive continuously. I mean, then the only thing is, it's like you can think of a square pulse, but I don't define the.
Is it not James-Cumming model?
No, it is James-Cumming, and because it's at a particular frequency, you can have this rotating wave approximation. Just give me a second. I'm getting a feedback here. How do I mute myself? No, I'm getting a feedback. I don't know. Okay, nice.
You can use your volume.
Okay. Okay, so yeah, so I'll show you how this external driver appears and the bath appears now. So in the lab frame, you have these displaced thermal states interacting with the qubit. Okay. Now we go to a special frame known as the displaced interaction frame, where we go to the interaction frame with respect to the field Hamiltonian, the bare Hamiltonian of the field, and we go to the displaced frame with the d alpha. So here what happens is, you see the Hamiltonian looks like this now, where you have the bare Hamiltonian, the qubit, you have the same driving Hamiltonian that we saw previously, and we have an interaction with the thermal states of the bath, because in the displaced frame, this displaced thermal state looks like just the thermal states. You remove the displacement from the state and put it into the Hamiltonian. That's it. So this is what you have, and this displacement is what is causing the drive to appear on the qubit, essentially, if this is okay. So here you can have that the dynamics of the qubit and the field is, of course, described by this equation, the one Neumann-Liouville equation. And in this interaction picture, the interaction Hamiltonian, the V of t, is given by such a formula where, if you remember in Maria's talk, we defined these temporal modes with which the bath interacts with the qubit. Okay, so these are temporal modes of the bath interacting with the qubit. And they are basically, this is de-exciting the bath at position 0 at time t, and exciting the qubit. Sigma plus is exciting the qubit. And that's how it's defined. Yes. So now what we do is, if you remember Alexia's talk, Leah's talk, we want to separate out the effect of the correlations, essentially, from the reduced dynamics of each of the subsystems. So we do that. At each time, the correlations can be separated. And this is a unique definition where chi can be defined by just subtracting rho SF from rho S times rho F. Okay. With this separation, what you see is an additional term that appears in the commutator in the reduced dynamical equation of the qubit. Okay, this curly HS that I've defined. Now, this curly HS is important because it has the effect of the subsystem of the field instead, that is driving the qubit. You see, there's a trace over the field with the state of the field and the coupling term. So this is, you can think of it as an external driving because of the reduced state of the field. Okay. And this, now the thing is, I've shown you that the qubit actually does follow the optical Bloch equations. So these two equations are actually the same, just that I've separated the effect of the correlation in the second equation, right? So the difference comes from the dissipator, which actually can be written as this commutator with this driving term and the correlation part, right? So this is basic, the sum is the dissipator of the OBE. And yeah, so the dissipators differ by the driving term HS, and I'll show you what HS is now. So if you remember, Alexia talked about these input-output relations, where this is something that's very standard in quantum optics. But here we do this in the interaction picture, okay, where each temporal mode can be written as the input mode of the field plus the coherence of the qubit. Okay. Now the thing is, we are in a displaced frame where the input states are thermal for the field. So here, the first moments of the field for thermal field is 0. So this part goes to 0. What we are left with is something that is the self-drive now, because that gives the self-drive because it is the coherence of the qubit itself. So this, we call this term that comes from the dissipator the self-drive, because its amplitude actually depends on the coherence of the qubit itself, as you can see here. Because this HS depended on the coupling term, which had these temporal mode operators. Now these temporal mode operators, because they can be written as in terms of the coherence, it appears in the self-drive, and that is why it's called the self-drive. Okay, so this is important. And now that I've talked to you about the dynamics, and the first difference that comes because of the way we are really analyzing the problem is because this self-drive. So what are the energetic consequences of the self-drive is what we are going to show next. So before that, I will talk to you about the bipartite quantum energetics, which you have already seen many times now. But just to recap, okay, the internal energy of the qubit or the field, because it is a symmetric approach now, so M can be S or F, is defined using the bare Hamiltonians itself. Okay, and now this the internal energy flux is decomposed again into the correlated and uncorrelated part, where the correlated part gives you the work flux, and the uncorrelated part gives you the work flux, and the correlated part gives you the heat. So this is again in a very similar approach to the open approach. We define it like this, but we have the state of the field now in our definitions, okay, and the correlation. So, and this driving term can be defined for both the qubit and the field, as you can see here. It could be the qubit driving the field or the field driving the qubit. That is why this is a bit symmetric now, because we can define work or heat for the fields itself. Okay, so this is the first law. I'll be talking about the first law for a while. So we have,
can you go back to the previous slide? What kind of trace are you taking? Trace L not equals to AM on the left hand side.
Here, this is basically, so M can be either S or F, let's say. So if it's S, the other subsystems that are there. Okay. So yeah. So basically you have the other subsystems driving your the subsystem you're looking at. And that's what this is saying. Everything fine till now? I'll move. So talking about the first law, we have the energy conservation, where the internal energy of the qubit plus the field, plus now there is a coupling energy term that comes here, which sum to 0. Okay. The coupling energy is essentially the average of the coupling Hamiltonian, the V of t, plus of VSF from the Schrodinger picture. Okay. Now at resonance, what we see is that this V of t goes to 0. And this is also with the slowly varying envelope approximation that I'm not going to details, but yes, there are some assumptions under which the coupling term goes to 0. So in this case, what we get is that the internal energies are balanced, the works are balanced, and the heats are the bipartite work and bipartite heats are balanced. Now the nomenclature uses bipartite work and bipartite heat for the bipartite quantum energetics and work and heat for the open approaches. Okay, because this is a comparison, this is important. Okay, and when for general inputs, when this coupling term is not 0, we get another balance equation, but now the bipartite work summed with the uncorrelated part of the coupling term now. Okay, and you can define these, and it's given here. You take the derivative of the coupling term, and then you you separate out the correlations, and that's how you get these. Okay, so of course, because the bipartite works only depend on the uncorrelated parts, so you get the uncorrelated part of the coupling energy coming here, and this summing to 0, and similarly for the bipartite heat. Okay, these are just definitions for now. A lot of definitions I know, but sorry. Yeah, so now we are done with the setup. Now the main comparison comes up. Any doubts till now? It's okay. So now we compare the first laws first. Okay. So before really doing the comparison, let's start with a very simple scenario where we have the qubit not in the ground state, in any state other than the ground state, and that the external field is vacuum. So that's it. So essentially what you have is a dissipation equation, and that's it, right? Where alpha is 0, the temperature is 0. It's basically a qubit interacting with a 0 temperature bar. So in the open approach, the work, of course, the work flux is 0. There is no work done during dissipation, right? But what you see, if you separate out these correlations, what you see is that this self-drive actually gives some self-work which depend on the coherence of the qubit itself. So there is some work being done during a dissipation process. To not make it sound too weird, the way I like to think about this is, imagine like the qubit on the Bloch sphere, on the surface of the Bloch sphere in any state. Now, during dissipation, what happens is, of course, the qubit, the radius of the qubit reduces. It goes into the Bloch sphere. But that's not the only thing that happens. What it happens is also it turns on inside the Bloch sphere. So it reduces radius and turns. What the self-drive is trying to do is get to analyze, to account for this effect of the turning inside during the dissipation, right? So that is the unitary that is, turning the qubit inside the Bloch sphere, and that effect is taken into the commutator now. And this commutator is giving you the unitary evolution. So this self-work is the energetic counterpart of this unitary evolution that happens during the dissipation process, right? And here, what we see is that if we rather apply the bipartite work, it becomes this self-work. So if there are two ways of thinking about this. One is you apply bipartite quantum energetics, you'll see that, okay, there is some work done and it depends on the qubit coherence. The other way of thinking about it is there is some external driving happening, which is turning the qubit, and the rate of change of this drive, the average of that is some work, flux, that appears here. This is the self-work, okay? And this self-work has been dubbed spontaneous emission work because this is during spontaneous emission. And it has been measured also in this paper by Juliet, the energetic cost of work extraction. Proposed, sorry, the measurement has been proposed, sorry. Yes. I'm sorry, yeah. Yes. Okay. So let's step up a bit. Let's go to a more difficult case than just the vacuum. We are in a resonant case. The field is in resonance with the qubit. And here, again, I apply all the approximations so that the coupling term is 0. Okay. So here what happens is the internal energy, the way we defined for the qubit, is the internal energy the way it is defined for the open approaches. Okay. Now, even though the internal energies are the same, the works differ, of course. The works and the heats, they differ. The difference arises, of course, due to the self-drive term, okay, because there is this self-driving that is happening inside the qubit itself, right? So what you see is that the heat, because the self-drive term came from the dissipator, this heat minus, if you take out this energy because of the self-driving, it is the bipartite heat that you will get. Whereas if you add this term to the work, to the open work, you get the bipartite work that is done on the qubit. And that is what happens in the resonant case. And this self-work really relates the works and the heats of the two approaches. Okay. Now for highly intense coherent fields, where you don't form correlation, essentially, your work, the self-work goes to 0, and then the frameworks match. Okay. So in the classical limit, the frameworks coincide, which is a great thing. So good. Now we step up again. We go for the non-resonant case. So this is completely new. So in the non-resonant case, the coupling energy is 0. So now here some interpretations change already at the level of internal energy. If you look at the internal energy of the qubit in the open approach, it is defined with the bare Hamiltonian plus this coupling term. So the coupling energy is included into the energy of the qubit itself. That's what this does. And this is one point of asymmetry that happens in the open approaches, that the coupling term is included in the bare energy of the qubit, and well, that's what happens. But here, what we see from the bipartite approach is that this actually, from using the energy conservation, you see that the internal energy, the way it's defined in the open approach, is the negative of the field energy that is defined in the symmetric, the bipartite approach. You see? So the internal energy is basically all the energy given by the field. It's okay. Yes. So yeah, the internal energy of the qubit, this is something I want to emphasize here. If you do the calculations, the internal energy of the qubit depends on the populations, the way you define in the bipartite approach, in this scenario at least. And the coupling energy only depends on the coherences instead. Okay, this will be important later. Yes. So another point of difference that comes is, of course, on the definitions of the work and the heat. So here, the self-work is the difference between the bipartite heat of the field and the energy change of the bath. That's the minus Q. Okay, or the thermal part of the field. Okay, so this is how in the non-resonant case the self-work is interpreted. It's really the you take the bipartite heat given to the field and subtract from it the energy change of the bath, or minus Q dot, and that's what is self-work. Or also it can also be thought of as the work done by the field plus the work of the open approaches. The bipartite work done by the field and on the field, and the work in the open approaches. So that you can see here. Okay, and all of this is essentially because the field is coming into play now, into the self-work done on the qubit. It is an immediate energetic consequence of the separation of the self-drive term from the dissipator. So you really split, write the dissipator plus this self-drive to get the correlation part that comes in the reduced dynamical equation. So that's what we see here. And that's one of the points where this the difference arises, essentially. Okay, so now I talk about are there any doubts in the first law part? Okay, so now the second law, and
I have to think about the question more clearly. I come back.
Okay. So the second law part is a bit short, and yeah, so I'll go through it anyways. So we are calling something known as we call it the closed second law. Okay, so we saw that in the open approach, you can of course define the second law because there is some bath which we trace over, we lose some information. So we have that the von Neumann change the von Neumann change, entropy change. My God, sorry, I need water maybe. Yeah, the von Neumann entropy change of the qubit minus the temperature times the heat is greater than 0. Thank you so much. Okay, and in our approach, one sec. Thank you. Yeah. So like the open approach, we can get a bound on the change of the von Neumann entropy using the bipartite heat of that's given to the field instead. And this is the way we make we form the bound, and this bound is true. The thing is, the interesting part about this bound is that it's tighter. It's a tighter bound than what you get from the open approach. And this is because the bipartite work done on the field is always greater than the energy change of the thermal part. So it's a tighter bound on the change of the von Neumann entropy. And this is also because the self-work term, as it turns out to be always negative. As you saw, it was negative of the modulus square of the coherences. And this is one way of thinking about it, that the self-work is always negative. So this bound is always tighter if you take out the self-work from the heat instead, from the open heat. And the way, so if you remember, Alexia made a small point in the first day, saying it really things depend on the entropy production depends on the protocols that you have. So the way I think about this is, and this is, of course, it's open to debate. The way I think about this is, all you're doing in the open approach is you're cutting the correlations. In the closed approach is that you're cutting the correlations. While in the open approaches, you are removing the state of the bath itself. You're losing all the information of the external systems that are not the qubit. So this is one way I think about it. That's why you get a tighter bound for the entropy production sense. I don't want to call it entropy production because you might argue, okay, this is isolated system. You have unitary that you're doing unitaries. You can always do a U dagger and come back. And so where is the entropy production? right?
Yeah, but that's in the partition.
Yeah.
Once you impose a partition, that means you can't do a global measurement. So there's only
Yes. Yeah. So yeah. So this is the partition here is like cutting the correlation for me. It's like, yeah, you can only do local unitaries afterwards. Okay. So we get this tighter inequality. I wanted to end the talk here, but there is also another section that I had prepared. But if all of you are not sleepy, I can present that, or else we can end by saying the second law is tighter for the bipartite approach and done. Or else there is also a part about the quantum and classical separation. Or else when the paper comes out, you can read it there. It's totally fine. What shall we do? Do you think? Is it?
So I have to go teach,
So maybe I conclude.
okay.
Yeah, it's we have time. Yeah, okay. I conclude quickly and get done.
And maybe you can go into it in the questions, but yeah,
Sure.
why don't we?
Okay, so in the conclusion, I just want to say that the bipartite quantum energetics gives a detailed energetic analysis of isolated systems. So initially we motivated BQE. BQE is bipartite quantum energetics, and we, in a sense, close the optical Bloch equations by specifying a particular initial state for the field and the kind of interaction that happens and things like that. And we compared this bipartite quantum energetics and with the 1D atom, and saw that there's this self-derived term that comes in, and there is this change of internal energy definition that leads to the energetic to the differences in the energetic quantities. And we also saw that with the bipartite definitions of heat and work, we get a tighter bound on the change of volume and entropy of the cube. Yeah. So the outlook for this, I would say, would be really to think about the kind of protocols we can have to extract this work, for example, or in which situations is it really useful to define these quantities. And because these quantities, as we mentioned, like it's measurable. The work and heat are really, you can make experimental setups where you can easily measure work and heat, which is not always possible in the open approaches, right? It's not very easy to measure the work and heat of the open approaches. So yeah, these are the references. Thank you. If you have any questions, this is my email ID, and that's it. Thank you.
Yeah, I just wanted to thank everyone for coming.